In the heart of this untamed wilderness, where water rushes forward with a force equal to thousands of bombs, mankind decides to wage its greatest battle against the laws of physics. Here, engineers will tame this aquatic beast by building a fortress of concrete that will transform the face of the Earth forever. Because this choice is not random, it requires a complex mathematical process beginning from space, where terrain is scanned down to the centimeter, to identify the bottleneck, that precise point where the valley narrows to increase hydrostatic pressure and save millions of tons of materials. Before pouring a single drop of cement, geologists descend like mountain climbers to examine the bones of the Earth. The rock here must be as solid as granite, free from faults and cracks that could trigger a catastrophic collapse under the weight of billions of tons. Beneath the riverbed lies the greatest danger, where seismic surveys and sound waves create a three-dimensional map of the Earth's layers, ensuring that foundations won't slip or sink when the dam's weight reaches toward the sky. Meanwhile, in planning rooms, dreams transform into numbers, equations of stability, dead load calculations, and earthquake resistance. Here, every figure represents a matter of life and death for thousands of people who will live behind this giant wall. Then the logistical epic begins, cutting roads through mountains untouched by human feet, while fleets of massive trucks and excavators crawl toward the site, announcing the start of an engineering war against this harsh terrain. But how do you build in the middle of a raging river? The answer lies in the grand engineering trick, diverting the course. You cannot stop the river, so you must force it to bypass through giant tunnels carved into the heart of the mountain. Massive tunnel-boring machines, mechanical beasts weighing hundreds of tons, begin devouring rock. These aren't mere pipes. They are artificial arteries, wide enough for a commercial airliner to pass through, designed to contain the river's complete fury. Precision in blasting is key. Explosives are planted in an exact geometric pattern to shatter rock without damaging the surrounding mountain's structural integrity, a dangerous dance between gunpowder and geology. Once drilled, tunnel walls must be immediately reinforced by spraying shotcrete at high pressure, coating the opening with a solid shell that prevents collapses and transforms the mountain cavity into a safe water passage. Then comes confrontation. Trucks begin dumping giant boulders into the river channel to build a temporary dam, a fierce battle to cut off the water's artery and force the current into prepared side tunnels. In a moment of engineering triumph, the river changes its ancient course. Water surges toward the darkness inside the mountain, leaving the old riverbed to dry slowly and reveal the stage where the greatest structure will be built. But the battle isn't over. Massive pumps work day and night, sucking up muddy water and suspended sediment. The construction site must be completely dry. Concrete and mud are sworn enemies. Reaching the bottom isn't enough either. You must dig deeper through millennia of silt and sand to reach bedrock. Foundations aren't built on sand, they're anchored into the solid Earth's crust. Now, facing this open wound in the valley's body, the preparation phase is complete. The site has been tamed, and the stage is ready to receive millions of cubic meters of concrete that will defy time. Since cleanliness here is not a luxury, but an engineering necessity, the base rock is washed with incredibly high-pressure water hoses to remove any dust particles that could form an insulating layer, preventing concrete from bonding to the earth. Beneath the dam, the ground isn't completely solid, so curtain grouting begins. Excavators drill deep into the earth, preparing to inject a liquid cement mixture that seals any microscopic cracks. This liquid mixture seeps like glue into the earth's veins, hardening to form an invisible curtain, preventing future water seepage under the dam, protecting the structure from destructive hydraulic lift forces. Any cavities or protrusions in the rock are treated with dental concrete, a precise operation to completely level the surface, ensuring the dam's enormous loads distribute evenly across the rock base. Before construction, an electronic neural network of precise sensors is embedded in the foundations. They'll remain there forever, monitoring the Earth's pulse and any seismic movement threatening this concrete giant's safety. Next, the skeletal structure takes shape. Massive steel reinforcement cages are lowered, each rod as thick as a man's arm, interlocking with the rock, creating an eternal bond between nature and engineering. In a sleepless night, the first pour begins. This isn't mere pouring, it's laying the cornerstone that will support an artificial mountain. Concrete flows like cold lava to fill gaps. The mixture here is highly secretive, using low-heat cement and special additives to reduce violent chemical reactions, since traditional concrete might crack under this enormous thickness. Because air is the hidden enemy, armies of workers use giant mechanical vibrators to expel air bubbles from the wet mixture, ensuring maximum density and unbreakable strength. Layer after layer, the valley bottom disappears beneath a gray, solid blanket. foundations rise slowly and deliberately, with each layer hardening and gaining strength before bearing the next layer's weight. Within this solid body, inspection passages called drainage galleries are formed passages that will allow engineers to enter the dam's heart later to monitor leaks and structural health. As work continues, the chemical reaction hardening concrete generates enormous heat capable of boiling water. Thermal cameras monitor this industrial fever because any uncontrolled temperature spike means catastrophic cracking. The solution lies in internal cooling. Thousands of kilometers of metal pipes are embedded within the concrete, allowing chilled water to circulate, absorbing reaction heat and keeping the dam's core cool. The dam isn't poured as one piece, but as separate blocks interlocking through shear keys, engineered protrusions and zigzags, preventing blocks from sliding over each other under water pressure. Precision reaches the millimeter. Laser devices scan each completed layer. There's no room for error in flatness. Any miscalculated tilt in the foundation multiplies its effect hundreds of times by the time it reaches the top. The base is complete. What was a rugged valley is now a colossal concrete platform stretching mountain to mountain, ready to support the upper structure reaching toward the sky. Now the vertical phase begins, with giant steel forms, each weighing dozens of tons, raised to shape the first walls. These forms give the dam its curved, pressure-resistant shape. The forms are coated with special chemicals preventing concrete from sticking, ensuring a glass-smooth surface when removed, vital for later water flow. Between each concrete block, rubber, water stops are placed flexible strips, serving as the last defense against water seeping through natural expansion and contraction joints. In the sky, cable-stayed cranes dance, with enormous buckets carrying 9 cubic meters of concrete each flying across the valley, guided by wireless precision to land exactly where needed. From the suspended control cabin, workers look like ants, but control here is absolute. One wrong move means crushing the crew below under tons of gray mixture. Meanwhile, reinforcing steel never stops, growing like tree branches with rod ends left protruding to connect the current layer to the next, creating structural continuity from bottom to top. In field laboratories, concrete samples are tortured until collapse. Each batch must prove its ability to handle fantastic pressures before being poured into the dam's body. Because nature doesn't surrender easily, storms and rain attempt to ruin the fresh mixture. Emergency teams rush to cover and protect the pour. Excess water weakens concrete and destroys its strength. Work never stops. Welding sparks cascade, lighting the valley's night as workers continue binding steel and preparing forms for the next cycle, a frantic race against the schedule. Construction follows a checkerboard pattern. Separate blocks are poured with gaps, allowing concrete to shrink and cool from multiple sides before returning to fill the gaps, a strategy avoiding thermal cracks. Before pouring new concrete over old, the surface is sandblasted to remove the smooth shell and expose gravel, ensuring strong mechanical bonding between successive layers. Heavy plumb lines suspended in special wells, running the dam's length monitor vertical straightness with extreme precision. Any slight deviation threatens the dam's balance when it fills. The giant begins showing its head. The wall now clearly rises above the riverbed, a visual barrier cutting across the valley, announcing the end of the foundation phase and the start of the elevation battle. The foundations are laid, but the real challenge has just begun. What's been built is merely the feet. Now comes building the body, carrying an entire lake's burden on its shoulders. To feed this beast, a complete concrete factory was built on site. Conveyor belts constantly transport mountains of aggregate and sand, mixing in precise amounts, producing thousands of tons daily. Inside giant mixers, the chemical battle rages. Water, cement, and coolant ratios are adjusted with pharmaceutical precision. Any measuring error means dam weakness that cannot be repaired. On hot days, crushed ice is added directly to the mixture. Pre-pouring concrete cooling ensures slow, uniform hardening, granting it diamond-like hardness. Number the dam. Engineering marvel. With elevation comes the curved shape of the dam, and this curve isn't for beauty. It's an engineering genius that transfers the enormous pressure of water to the rocky shoulders of the mountain. Instead of relying solely on the dam's own weight, stress maps show how forces are distributed. The more water pressure builds, the more the arch compresses and bonds with the mountain, using the water's own power to lock the structure in place. Then, the sliding formwork system begins operating. These mechanical molds climb the wall automatically and slowly, allowing for continuous pouring around the clock without needing to be dismantled and reassembled. Deep inside the wall, giant steel pipes called pressure tunnels are embedded the arteries that will blast water with tremendous force toward the turbines. These must be installed with absolute precision. The welds on these pipes are inspected with X-rays, and not a single air bubble is permitted in the welding, because water flowing here at such pressure could tear steel apart if it finds any weak point. Encasing the pipes in concrete is a delicate operation. You must balance internal and external pressure so the steel pipe doesn't get crushed under the weight of wet, heavy concrete. To increase load-bearing capacity, engineers use post-tensioning technique. Steel cables inside special channels are pulled with tremendous hydraulic force after the concrete hardens, compressing the structure and making it one solid, cohesive mass. With each meter of elevation, the risks multiply. The winds here are stronger, and a fall means certain death. The dam is now rising hundreds of meters, becoming a wall that separates two worlds. On the front face, intake towers stick out, structures that will serve as gateways for water, equipped with giant screens to keep trees and rocks away from the sensitive turbines. Massive steel mesh networks, called debris barriers, are installed shields that will stand against everything the river sweeps up, protecting the dam's mechanical innards from destruction. On the side, the spillway takes shape the safety valve, a giant concrete slide designed to drain excess water during flood season and protect the dam from overflow at its top. The spillway surface must be smooth as a mirror, because any roughness could trigger cavitation, where water bubbles explode and eat away at the concrete like concentrated acid. To fight cavitation, engineers add ventilation slots in the spillway that pump air beneath the fast-moving water stream, creating an air cushion that protects the concrete from destructive friction. Before approving the design, they tested it on miniature hydraulic models, where colored dyes revealed water whirlpools and flow speeds, ensuring the kinetic energy of water wouldn't rip out the dam's foundations at the bottom. At the spillway's end, a stilling basin is built where concrete blocks with teeth break the water's wild energy, taming the roaring waterfall and returning it gently to the river's course. Then, the spillway's massive steel gates, arched gates that will control lake level and open automatically in danger to release millions of cubic meters in seconds, are raised. Hydraulic jacks, the size of cars, are installed to move these gates, mechanical muscles that must operate precisely even under pressure from tons of surging water. When the dam reaches mid-height, engineers measure deflection and ask, is the structure moving as the computers predicted? Any deviation from the digital model requires immediate shutdown and investigation. Inside the dam's core, elevators connecting top to bottom are built not ordinary elevators, but vertical transport vehicles that penetrate hundreds of meters of concrete and darkness. The network of internal tunnels expands into an underground city. Kilometers of passages, stairs, and equipment rooms make the dam a living being you can walk through like its veins. After concrete blocks cool and shrink, it's time for joint grouting, where cement mortar is pumped under high pressure into gaps between blocks, bonding them and turning the dam into one solid piece. The summit approaches. The wall that began at the valley bottom has become a tower touching the clouds. Work now focuses on forming the crown, the road that will run across the dam's top. From the air, the arch appears complete, an elegant curved line of white concrete cutting through brown and green nature, proof of planning precision and construction power. Barriers and lighting are installed at the top, and soon cars will pass here, oblivious to the engineering miracle beneath their tires and the millions of tons of concrete carrying them. Meanwhile, the cranes that built this monument begin leaving. Dismantling these giants is itself an engineering feat, lowering their pieces carefully from towering heights. Final inspection of the water-facing surface happens as teams of climbers check every square meter of the exterior, because any crack or defect must be fixed now before it disappears underwater forever. Sensitive areas get additional protective coating as layers of epoxy and polymers are applied to strengthen the concrete's resistance to water erosion and dissolved chemicals. At the dam's base, the powerhouse is built. This massive building will contain the project's beating hearts, turbines and generators that will turn water's force into electricity. Here come the giant turbine pieces, each weighing hundreds of tons, requiring special transport vehicles with hundreds of wheels to distribute the load and protect them from warping during transport. Inside the powerhouse, mighty bridge cranes lift the spiral casing. This helical steel shell will spin the water around the turbine to ensure it enters from all angles equally. Welding the spiral case requires surgical precision. The steel is very thick and must be heated before welding to avoid thermal shock. It's a process taking weeks of non-stop work. After fastening the spiral case, it's buried in concrete because the concrete shell around it must be thick enough to absorb massive water vibrations without transmitting any to the rest of the building. Below the turbine, a draft tube. This expanding cone is installed to slow the outgoing water's speed, recovering some pressure and significantly boosting turbine efficiency. Then comes the critical moment, lowering the runner. This giant stainless steel fan will take water's direct hit and spin with the power of thousands of horses. The runner's blades are designed with superior aerodynamics and coated with erosion-resistant materials, because water speed here could tear ordinary metal apart. Yet these blades are built to last decades. The rotation shaft steel and the generator's backbone connects the turbine below to the generator above. Its balance must be perfect because any vibration at maximum rotation speed will destroy the station. On the upper floor, building the stator begins, with thousands of copper coils stacked with manual precision. Here, electricity will be generated when the magnetic field cuts through these wires. The project's biggest lifting operation happens, lowering the rotor. A giant magnetic disc weighing hundreds of tons that slides inside the stator with only millimeters of clearance. If the walls touch, it's catastrophic. Engineers measure the air gap with precise instruments. This tiny space is where the magic happens, where mechanical motion transforms into silent electrical energy. Then the generator connects to massive bus bars, not ordinary wires, but aluminum or copper paths, thick as tree trunks, carrying electrical current strong enough to light a city. Because generators produce heat hot enough to melt them, complex air and water cooling systems are installed that constantly circulate around the coils, keeping them at safe operating temperature. Next, the brain is prepared, the central control room where data from thousands of sensors pour in, with screens and servers managing water flow and electricity production at the push of a button. The dam's nervous system, completes with miles of fiber optic cables transmitting data at light speed, is necessary to sync turbine movement with the national power grid. Outside, giant transformers are positioned, their job raising electricity from thousands to hundreds of thousands of volts so it can travel through high-tension lines with minimal loss. High-voltage cables connect the dam to the outside world. These are the umbilical cord that will carry the river's power to run factories and light homes hundreds of kilometers away. Extreme safety tests run, preparing for what might happen if something fails. Emergency shutdown systems that can disconnect turbines and stop water flow in fractions of a second are tested to protect the plant. Gas and water mist fire suppression systems stand ready because a generator fire is a nightmare. The response must be instant and automatic without human intervention. Even giants need beautification, so final touches are applied to the power station's facade to make it an architectural landmark, reflecting the engineering marvel inside. Surrounding slopes are stabilized and replanted. Restoring vegetation isn't just for looks, but to anchor soil and prevent erosion that could silt the reservoir later. The temporary city where thousands lived begins fading away. Offices and homes are dismantled, leaving the stage for the lone hero, the dam. Professional divers descend one last time to inspect water intakes. This is the final chance to see these parts with human eyes before the reservoir's deep waters submerge them. The moment of truth arrives. The massive steel gates of the diversion tunnels begin lowering, and the river's side escape route will be blocked, forcing it to confront the wall built to intercept it. The river crashes against the barrier. Water begins accumulating. The level rises with terrifying slowness. The reservoir is forming. Pressure on the dam begins building gradually. Sensors cry out with numbers. Millions of tons of water pressure now press on the concrete. Engineers watch the screens with pounding hearts, wondering, will the theory hold up against reality? The concrete absorbs water. Fine pores fill. The dam's total weight increases. This saturation is expected, calculated, part of the structure's stabilization process in its new environment. As water rises, animals have less land. Rescue teams work to move wildlife to safe areas, trying to maintain ecological balance in the new region. The old valley drowns trees. Roads, perhaps abandoned villages, disappear beneath the sparkling water surface. A whole world gets buried, so a water reservoir can be born to ensure life for millions. In the depths, engineers monitor seepage. Small amounts of water should pass through the foundations to relieve pressure, but if it exceeds the permitted level, there's a problem with the grout curtain. The reservoir reaches half capacity in a majestic scene of vast water surface, stretching to the horizon, a strategic reserve of fresh water that changes the surrounding region's climate. Pressure gate testing comes next. They're raised slightly to let water enter and fill the pipes. The roaring water sound rushing into empty pipes, thunders like thunder. When water reaches the turbine, slow rotation begins. This first impulse is the moment of the plant's birth. Engineers listen for any friction or abnormal clicking sounds. Speed gradually increases to synchronous speed, and the turbine, weighing hundreds of tons, now rotates with lightness and grace, balanced like a spinning nightingale. Then current is injected into the field coils. The magnetic field forms. On screens, the voltage indicator jumps. The generator is now alive and ready to give. The precise synchronization phase arrives. The dam's electricity wave must match the national grid's wave exactly. Any timing error causes electrical explosion and equipment destruction. In that historic moment, a finger presses the circuit breaker closure button, and in a fraction of a second, the circuits unite, and energy flows from the river through the nation's wires. Shouts of joy rise up in the control room as years of planning, construction, and hard work culminate in this moment, and the river illuminates the city. For miles away, lights flicker on, factories hum to life, and energy pulses through the veins of cities, all thanks to the power of water that has been tamed here. But the work doesn't stop at one turbine. Instead, other units are brought into service one by one, raising the power station's output to its maximum capacity, transforming it into a fortress of clean energy. Under full load, thermal cameras monitor the transformers, which must withstand the heat generated by millions of watts flowing through without failing. The reservoir fills completely, water touches the spillway's edge, and the dam now operates under its maximum design load. The concrete mountain strains under pressure, but doesn't budge. Then comes the spillway test. Gates open, and a massive arc of water launches into the air in a breathtaking display of nature's raw power bending to the engineer's will. Water spray creates clouds and rainbows that decorate the valley. Here, beauty conceals devastating kinetic energy that's intelligently dispersed in the stilling basin below. From above, the dam appears as a thin line separating the deep blue of the reservoir from the dry valley behind it, a stark contrast that illustrates the weight of responsibility resting on this wall. Hairline surface cracks may appear, which is normal, but maintenance crews constantly monitor them to ensure they don't expand. Maintenance here is a lifelong ongoing process. In the dark depths, robotic submarines inspect the dam's submerged face, while electronic eyes search for any erosion or deposits that could threaten the intake gates. Giant mechanical arms work to clear debris, barriers, trees, and logs swept by the river are regularly removed to ensure water flows freely to the turbines. Silt is the slow enemy. Over time, sediment accumulates and reduces the dam's storage capacity, so silt levels are monitored to plan dredging operations or open the lower sluice gates. These lower gates open, releasing a thick black current from the dam's base, carrying sediment to clean the reservoir's depths and extend the dam's lifespan. We haven't forgotten nature either. Fish ladders and water elevators function to transport migrating fish across the dam, an attempt to heal the wound that construction inflicted on the river's life cycle. What was once a forbidden construction site has become a tourist destination. People walk across the crest, amazed by the scale of achievement, unaware of the enormous complexity beneath their feet. Security here is strict. The dam is critical infrastructure and a matter of national security, with cameras and patrols guarding every corner. Any sabotage would bring catastrophic consequences for the entire nation. A full year's data shows brilliant success, terawatts of clean energy produced without burning a single drop of oil. The dam proves its economic and environmental value. Downstream, farmers enjoy steady water flow. Devastating floods and deadly droughts are now history. The dam tames the river, irrigating the land with wisdom and measure. Around the new reservoir, communities spring up, fishing thrives, tourism flourishes, agriculture prospers. The dam didn't just generate power, it created an entirely new economic zone. As the sun sets, the water's surface reflects deceptive calm, but beneath this stillness, turbines roar and concrete silently resists the pressure of mountains of water. The maintenance cycle never stops. One turbine is pulled for inspection, water erosion marks are repaired and polished, and the turbine returns to work with day one efficiency. After years, the Earth has completely settled under the dam's weight. Data confirms the structure has seated in its final position, becoming an inseparable part of the region's geology. If we rewind time, we'd see how drawings on paper transformed into concrete and stone, from the first blast in the mountain to the final drop of oil in the generators. It's a stunning comparison. The river that once flooded and destroyed has become a peaceful lake and a source of life. This is the essence of engineering, harnessing nature to serve humanity. But the price was steep. A memorial plaque preserves the names of those who lost their lives during construction. Their blood and sweat mixed with this dam's concrete, keeping their memory eternal as long as the structure stands. At night, the dam glitters like a jewel in the darkness, its lights a constant reminder of human reason's triumph and its ability to conjure miracles from rock. The smooth flow of water tells a story of balance between power and control, between need and protection. The dam isn't just a wall, it's a living, dynamic machine. Power lines stretching to the horizon are the arteries of life for modern civilization. Without these colossal monuments, our cities would sink into darkness and progress would grind to a halt. With each new sunrise, the dam continues its silent mission, and it will stand here for centuries, a witness to an age of giants. An engineering legacy passed down through generations, a symbol of human power when united with science.